All right, welcome back everyone. So as I mentioned before in this lecture, we're going to talk about the data that we get, in this case from cohort studies. These models can be expanded to other type of studies, but we're going to start with cohort studies. And just so you know, as you guys know from the beginning of the class, that I know it's sort of difficult to learn the math about these things through the computer. So we're going to do a combination of things. I'm going to go through this lecture. I've also posted some other YouTube videos from other people who show, their own way of teaching it, thinking that, for some of you may be able to relate to that. And then I'm going to make a series of the short videos to go through the calculation. So you should have, and then you're going to obviously do your lab assignments in a couple of weeks. So you'll be practicing these calculations. Okay, so let's start from the basics. So a contingency table or a 2x2 table is sort of the fundamental basic way that we start to think about exposure outcome relationships. And it's called a 2x2 because you have exposed and unexposed and diseased and non-diseased, and then you end up with 4 cells where each of these things cross. The totals, total column, total row, those are called the margins or the marginals. So it's sort of the sum of your columns or rows. But really the key here is understanding that we have this 2x2 table in here. And they're always set up the same way, or it should be. Your exposed is on the left side where we have exposed and unexposed, and your disease is along the top, disease, not disease. So this top right cell, which we labeled A here, is your people who are exposed, the number of people who are exposed who develop disease. Column or cell B, number of people who were exposed who did not develop disease. And then the margin here, our A plus B, this is the total number of people in your study who are exposed. So you can go through that. What was I going to say about this? So just make sure that when we're going through word problems, that you set up your table the correct way. That's incredibly important. The other thing, I'll get to that later, that's a little complicated. Okay, so here's our 2x2, the fundamental cornerstone of starting to calculate measures of association. So using our 2x2 tables, starting to fill them in with data from our studies, we can start to compare incidence. As I mentioned at the beginning of the first video in this week, what we can do with cohort studies, and hopefully you can now see this because you understand what a cohort study is that we have our exposed group. They develop disease over time. We can calculate what is the incidence of disease among our exposed group. We then have our unexposed group. We can calculate how much disease occurs in that group and calculate the incidence of disease in that group. And then we can compare the two. So let's start to go through some math. So the first calculation is going to be a cumulative incidence ratio. So basically all this is a ratio of cumulative incidence in the exposed and cumulative incidence in the unexposed. Sorry, I keep getting these messages. I don't know how to turn that noise off. Okay, so we're gonna calculate. So it's just a ratio. So the one thing to keep in mind, broadly, we're going to calculate cumulative incidence ratio and incidence rate ratio. So our two measures of incidence we can put into ratios. Broadly, those are called relative risk because it's the risk of getting a disease, the incidence of getting disease, relative to in your exposed relative to your unexposed. So in one of the videos, actually I think in both of the videos I posted from YouTube, they talk about relative risk, and it's broadly this idea of a ratio of incidence measures. So again, if we look at our cohort studies, the way we fill in these tables is that first we select our exposed group and our unexposed group, and then we follow them over time, and we can start to fill in these cells. So of our exposed group, how many developed our outcome? Of our unexposed group, how many developed our outcome? And then as you can see here, we can calculate from these cells cumulative incidence. You guys have done this before. So cumulative incidence among our exposed, the number with disease over the population at risk. These A's and B's are just based on the letters in the table. Then we calculate our incidence in our unexposed group. Number with disease number over population at risk. We now have two measures of cumulative incidence, one in our exposed group, one in our unexposed group. What do we do to calculate a cumulative incidence ratio? We simply divide. We put our cumulative incidence among our exposed group in the numerator and our cumulative incidence of our unexposed group in the denominator. And just be very careful that you always keep it that it's a ratio of exposed to unexposed. If we want to look at this in terms of the letters in our cells, you can see again A over A plus B in our numerator over C plus D in your denominator. What you then have is your cumulative incidence ratio, or sometimes you'll see this called a relative risk. It's the ratio of two measures of incidence. Okay, so some basic things about a relative risk. The null value is 0. What that means, or 1, I'm sorry, null value is 1. What that means is that if there is no association between your exposure and your outcome, you will end up with a relative risk or a cumulative incidence ratio of 1. Because what does 1 mean? 1 means that the incidence of your exposed was the same as the incidence of the unexposed. And when you divide one number by itself, you end up with 1. So if your incidence of in exposed group and your incidence in your unexposed group are the same, and you divide and you end up with 1, it means there's no association. People in your exposed group are not getting the disease more or less frequently than people in your unexposed group. Okay, so our null value is 1. If you see 1, no association. But values greater than 1 indicate that your exposure is a risk factor. So a value greater than 1 when you do this division means that there's a higher incidence in your exposed group than your unexposed group. That people in your exposed group are getting sick more often than people in your unexposed group. So your exposure is a risk factor for disease. The same thing happens the other direction. If your value is less than 1, it means your numerator is smaller than your denominator, and that the people in your exposed group are getting sick less often. So in that case, your exposure is a protective factor. So for example, right, say you're testing a vaccine and your vaccine is your exposure, and you're comparing the incidence of your disease among people who are vaccinated over the incidence of disease for people who are unvaccinated. Hopefully when you do that division, you end up with a number less than 1, and you can say, oh yay, my vaccine exposure is protective against disease. Okay, so I'm not going through a specific example of each of these because, again, I put them in the short videos. I figured it was much easier for you guys to dip into that and see how the math works than for me to struggle to do this on this platform. So if at this time you want to pause this video and go to the short video on how to work through some problems, you're welcome to. Or you can keep listening to me and go to the short problems later. Okay, so in the same way that we can calculate a ratio of cumulative incidence, we can also calculate a ratio of incidence rates, right? Again, the incidence rate, the way that it differs is that instead of our population at risk in the denominator, what our denominator is the person time. So if we look at our 2x2 table, in this case, our 2x2 table looks a little different. We don't have a column for have outcome and don't have outcome. We have a column for have outcome and person time. So the way we would fill in this table is we start our cohort study. We have our exposed group and our unexposed group. Over a certain amount of time you follow them, you're going to get the number of people who got your outcome, and then you're going to get the total person time accumulated among your exposure group. Then we do the same thing. We have our unexposed group. We have our number who developed our outcome, and then we have in this cell the person time accumulated in our group of non-exposed people. So previously when we calculated person time, we calculated it for an entire population. So you were able to get, just in general, what is the incidence rate of this disease in this population. Here you're really just splitting it. What's the incidence rate in our exposed group? What's the incidence rate in our unexposed group? Okay, so we can then, as you might imagine, the formula follows from there. So an incidence rate ratio, as I mentioned, this might also be called a relative risk, just generally, you'll see that places, is the incidence rate in our exposed group and over the incidence rate in the unexposed group. If we want to use the letters from our boxes, it's A over the person time in the exposed over C, right here, over the person time in the unexposed. Again, we're just comparing the incidence rate in our exposed to the incidence rate in our unexposed. Same things as with cumulative incidence. Our null value is 1, because what 1 means is that our incident rate in the exposed is the same as the incident rate in the unexposed. There was, being exposed was not a risk factor or a protective factor. Again, incident rate ratios greater than 1 indicate that exposure is a risk factor, less than 1 is a protective factor. Okay, so it's pretty simple if everyone takes a breath, keeps calm, looks, starts to figure out how to fill out their 2x2 tables, and you guys will have a lot of practice with that. All right, so this is a big deal. I'm going to actually zoom out for a second. So you can, I think everyone can do these calculations. It's just division. The real sticking point comes in, I find a lot of times with students, when we want to communicate relative risk. So you got a relative risk of 1.5. What the heck does that mean about the association between this chemical exposure and breast cancer, let's say? Okay, so I love this chart. I don't know how you do it, if you want to take a screenshot of this chart, if you want to go back into the PDF and pull out this chart, this is so helpful to me when communicating relative risk. So what we see here is that we have a relative risk of 1. That means the exposed and the unexposed are equally as likely to get the disease. There's a 0% increase of risk due to the exposure. But what happens if we get a relative risk of 1.5? You do that division, you end up with a 1.5. You could say that the people exposed are 1.5 times more likely to get your outcome, or they're 50% more likely. So up here is the way to move from this number to a percent. You just take away 1 and times 100. So same thing here. If you get a relative risk of 2, you can say something's associated with 2 times more risk, or the people exposed are 100% more likely to get the outcome. So hold on to this chart. Okay, so here are my examples. I'm not going to read through all of them, but pay attention, read through this on your own and pay attention to this language, because I'm going to ask you to write sentences. And it's super easy if you just have this language of how do I communicate relative risk. Now, the tricky part, not even that tricky, comes up when all of a sudden we have relative risks, either cumulative incidence ratios or incidence rate ratios that are less than 1. That sort of freaks people out. So say we did a 2-year study examining associations between pertussis vaccination and pertussis incidence. This is what I was talking about before when you're examining the outcomes of exposure to a vaccine. And you observed a cumulative incidence ratio or a rate ratio of 0.15. What do? It's less than 1. I can't do my -1 times 100 thing. So what we do is that we can flip it. So when a relative risk is less than 1, you subtract it from 1 to express the preventive association. So what we do here, I'm just going to go through this. Over 2 years, individuals who received a pertussis vaccination were 85% less likely to develop pertussis than individuals who are not vaccinated. So we had 1 minus 0.15 and times 100. So that's actually the same as above. Anyway, so just remember this, instead of 85% more likely, we end up with 85% less likely. That's the key difference when something is below 1. What you can also do is you can actually switch up your 2x2 table if it's more helpful to you. And you could say that the people who did not get the vaccination are actually the ones exposed. And then you're able to calculate a relative risk that's greater than 1. Either way, the key there when you start to switch who is my comparison group, who is my exposed and unexposed, is that you're consistent. You don't want to switch your 2x2 table so you're calculating the risk of pertussis if you're not exposed, and then communicate it that it's the risk of pertussis when you are exposed. Make sure to be consistent. I also wanted to point out here, I have in all these that likely is highlighted. So if you remember back, incidence is synonymous with risk, the risk of getting disease, And then that's also can be talked about in terms of likelihood. What is the likelihood of getting disease? So here, because we're calculating incidence, we can talk about more or less likely to get the disease. Okay, so those are two measures of relative risk. They are relative measures. They're comparing two groups and doing some division. There's also something called attributable risk. And this is a little more, let's just go through it. So we can do some different calculations that calculate attributable risk. And you actually see these much less often, and I'll explain why, they're actually much more useful in communicating the burden of disease. So with attributable risk, I'm gonna have to do it back up. We're asking the question, so instead of saying what proportion of how much more, let me try to think of this, so I say this. In the incidence rates and cumulative incidence ratios, we were saying how much more likely is something to happen when you're exposed. Here we're asking a slightly different question. We want to know how many cases of the outcome are attributable to the exposure. So, is the exposure to cigarette smoking are 100,000 per million cases per year because of smoking, right? It's about the number of cases per year that are caused by the exposure versus a comparison of your exposed and unexposed groups. Okay, so let's go through these because I do a pretty bad job explaining this all, I will admit. Okay, so the question related to this that we asked is, if we eliminated smoking, how many cases of lung cancer among smokers would we prevent, right? That's a pretty important question. So not just that smoking increases someone's risk by 2 times or 17 times is actually the number, but that if we eliminated smoking, we could prevent this many cases. So it's helpful to think, I actually really like these graphs because when I can't explain them, I go to these graphs and think about, right, there's always a level of background risk for a disease. As we learned when we were thinking about the multifactorial causes of disease, there are very, very few diseases where there's like only one cause. So there's essentially almost always going to be a certain background incidence of disease that are not attributable to your exposure, that they're happening for reasons other than your exposure. So that's what we end up with some cases of disease, even in our non-exposed group. But in our exposed group, when our exposure is a risk factor, we're going to have those background cases, those cases that would have been there even without our exposure, and then we're going to have this bump up. And this bump up is what is, attributable, what is due to our exposure. So here this graph is just showing you, they can divide out how much of the incidence is due to background risk and would have happened anyway, and how much incidence is due to exposure. And when we're calculating attributable risk, also known as a risk difference, you may see that some places, all we're doing, it's so simple, we are subtracting the incidence in our exposed group from the incidence in our unexposed group. And you're basically calculating that teal block, the number in that teal block, taking away this background risk number in the green block. Okay, so we'll go through, let me just make sure. Okay, here we go. So a difference between for attributable risk versus relative risk, here the null value is 0, right? So if your incidence in your exposed group is the same as your incidence in your unexposed group, when you subtract one from the other, you're going to get 0. So 0 means there's no association between your exposure and your outcome. And another important point is that your attributable risk or risk difference retains the same units as your incidence measure. So whether it's per 100,000, 10,000, that type of thing, you want to keep that. So let's walk through an example. So in a study of the association between hormone replacement therapy and breast cancer, the incidence of breast cancer over 5 years among women exposed was 82 per 10,000 women. Okay, so in our exposed group, we calculated an incidence of breast cancer of 82 per 10,000 women. Then the incidence of breast cancer in our women unexposed, so those who didn't take hormone replacement, was 40 per 10,000, right? So let's just stop here for a second because we can actually calculate a relative risk by dividing 82 by 40, right? So you'd end up with a relative risk of 2.5, I think. I think so. So you could have a relative risk of 2.5, right? But that's not what we're going for now. We want to know how many cases of the disease were attributable to our exposure. What is that bump up in cases beyond our background risk? So we're just going to calculate a risk difference, taking our cumulative incidence among our exposed, subtracting our cumulative incidence in our unexposed. Here we take 82 per 10,000 minus 40 per 10,000. You can just really subtract 40 from 82, and we end up with 42 per 10,000. So what this means is that among every 100,000 women who use hormone replacement, there are 42 excess cases of breast cancer over 5 years compared to women who do not use hormone replacement therapy. So this important point, and this is going to change later, is that we're looking among the women who use hormone replacement therapy, 42 excess cases of breast cancer are due to the hormone replacement therapy. There might be, there are other reasons why these women are getting breast cancer. So even though they're in the exposed group, that doesn't mean that all the disease is coming from the exposure. That even in the absence of this exposure, 40 cases of breast cancer would have happened, or we would expect to happen. Now, the key with attributable risk, right? We can calculate this even if we don't know this is a causal association. But ideally, we want to talk about how many cases of hormone replacement therapy did this exposure cause, right? So we're at a point where we can think about, okay, I feel like this is really a causal association. We have enough evidence to justify that. Then we can move from just saying there were this many more cases among women exposed than unexposed. We can really start to think causally and think about if we then took away that exposure and you took away the cause, we would prevent these cases of disease. So a causal interpretation, if you felt really confident that there was a causal relationship between hormone replacement and breast cancer, and it wasn't just some correlation, you could say, if women taking hormone replacement therapy stopped taking it, 42 cases of breast cancer per 10,000 women could be prevented over 5 years. So you're moving again from just saying it was associated with 42 per 10,000 cases of breast cancer to saying if we took this exposure away, we would save 42 cases of breast per 10,000, 42 cases of breast cancer per 10,000 women. Okay, hopefully you guys stuck with me on that one. So in addition to attributable risk or risk differences, there are other absolute measures of risk, and this is versus against relative measures of risk where we're doing that division that we did above. So we can calculate attributable risk percents, population attributable risks, and population attributable risk percents. I'm making a call right now that I'm not going to go through these at this point. I think that this is enough math to wrap your head around. But basically, these other absolute measures are basically, instead of just calculating number of cases that would be prevented, we can also calculate the proportion of cases that could be prevented in our women exposed. And then we can go to a different thing, which is in the entire population of women in the country, both those unexposed and exposed, how many cases and what proportion of cases would we prevent if we took away this exposure? So this is all about absolute number of cases that could be prevented if we eliminated the exposure. And the question is, are they being prevented just among women who are exposed, or are they being prevented in our entire population? And as you can imagine, this is an incredibly powerful thing to say. We don't calculate it that much, and we'll talk about this more because basically epidemiologists are lazy and it's our statistical software doesn't spit out these numbers. But how powerful would it be to be able to say, not just, okay, again, smoking increases your risk of lung cancer by 17%, but to be able to say, you know what? If we eliminated smoking in this population, we would prevent 50,000 deaths in our city, right? That's what attributable risk is telling us, and specifically population attributable risk there. Okay, so I'm going to speed through these. I'm happy to teach you guys these. Please send me an email if you want to learn them. but I find they're really important. I don't mean to devalue them. I think, and I want you to know the general idea of them, but the calculations get a little tricky in this online format. Okay, so let's sum this up. When would you use a relative risk versus an absolute risk? As I said, we often report relative risk. We often say someone's 2 times more likely or 50% more likely or whatever it is because our software spits that out. But an important thing to realize is that our relative measures are dependent on the sort of baseline incidence of disease among our unexposed. So let's say I'm just going to make this up off the top of my head, so we'll see how this goes. So let's say among our unexposed population, 2% of the population gets sick. And then in our exposed population, 4% of the population gets sick. So there's a 2 percentile point difference between what's happening in our unexposed group and our exposed group. If you divide 4 by 2, you end up with 0.5. No, 2. Sorry, 4 by, I was going the wrong way. If you divide 4 by 2, you end up with 2. I think my 6-year-old daughter can do that. And so you end up with a relative risk of 2. So whatever this exposure is, it's increasing your risk of disease by 2 times or 100%, right? Because we're going from 2% to 4%. What happens then if we go somewhere else sort of on the spectrum or on the, the spectrum from 0 to 1? So what happens if we say the baseline incidence of disease, the incidence of disease in your unexposed group was 50%, and then you similarly bump up your incidence of disease by 2 percentage points among your exposed to 52%. We're now dividing 52 by 50 and ending up with a relative risk of 1.04, dramatically different than 2. Instead of saying you're increasing your risk of disease by 100%, you are actually increasing your risk of disease only by 4%. But it's the same 2 percentage point difference in incidence. It's just because of where you started. You started with a rare outcome versus a common outcome. So relative risks can be really deceiving. And it all depends on the absolute level of risk. You know, people all the time, the media says like, oh, we just figured out that like eating pomegranates reduces your risk of this rare cancer by 500%. Well, what if your risk of that rare cancer was, 0.00005% anyway? Like, are you going to go and do a run on pomegranates and eat them, 1 a day? No, because you're probably going to say, oh, that's ridiculous. Like, I mean, if you like pomegranates, then go for it. But my absolute level of risk is so low, it doesn't matter that my relative risk was decreased. So the advantage of absolute measures is that regardless of where the baseline level of risk is, you're going to get the same answer, right? You're still going to get that something prevented 200 cases of such and such, no matter if it's a rare disease or a common disease. So for that reason, these absolute measures, and I'm talking myself out of skipping them, but I think you hopefully get the general idea of when we use them. That's important. These absolute measures are really important and communicate important information. All right, well, thank you guys so much. Go to the short videos to see the calculations being done, and I will see you next week.